Last video we discussed about the production of ultrasonics by the method of piezoelectric by using the piezoelectric generator. This is another important method of the production of ultrasonics by what is known as the magnetostriction method or the magnetostriction generator. In this video we'll be talking about this magnetostriction method and also the detection of ultrasonic waves, how they are detected. So what is this magnetostriction method? This is a method of generation of ultrasonic waves based on the phenomenon of magnetostriction. What is this phenomenon? It is a phenomenon which is exhibited by ferromagnetic materials. So as all of you know, magnetic materials can be classified into three types: paramagnetic, diamagnetic and ferromagnetic. We are not going into the details of all this. These materials are classified based on the nature and the degree of magnetization of the material when it is placed in a magnetic field. So ferromagnetic materials like iron and nickel, they experience a substantial degree of magnetization once they are placed in an external magnetic field. And inside these materials, tiny magnetic dipoles are arranged in the form of domains. Inside the domains, all these dipoles orient in the same direction. So when this ferromagnetic material is placed in an external magnetic field, what happens is these domains rotate, and because of this rotation, the ferromagnetic material gets magnetized in the same sense as the applied external magnetic field. So what is observed is that when a rod of a ferromagnetic material like nickel, or for that matter iron, is subjected to a magnetic field parallel to its length or is magnetized, it undergoes a small change in length. This phenomenon is known as magnetostriction. Why it happens? It happens because of the rotation of the domains inside the ferromagnetic material. Because of this rotation, a strain is produced, resulting into a slight increase in length. This increase in length will not be visible to the naked eye. It's very minute. So this phenomenon is known as magnetostriction. This change in length depends on the intensity of the applied field and the nature of the material of the rod. Means, if the strength of the applied magnetic field is more, the change in length will be more. It can either increase or decrease depending on the type of the material. Suppose nickel is a ferromagnetic material, also iron is a ferromagnetic material. The amount of change in length and the nature may vary depending upon the material. Also, the change in length is independent of the direction of the applied field. So, instead of a direct field, if I apply an alternating field, that is what we are coming to, the change in length is independent of the direction of the applied field. Now that is what I was talking about. If an alternating magnetic field is applied, the rod will undergo a change in length for each half cycle of the applied AC. Means we have, let me say, an AC magnetic field. Alternating magnetic field means it increases in one direction, comes to zero, increases in the other direction, comes to zero. So when it is increasing in the positive direction, the rod will increase in length, and when the field comes to zero, it will come back to its original position. Again, when the field increases in the reverse direction, the rod will again show an increase in length and come back to its original position. So, by that time, the alternating magnetic field, it completes one whole cycle. The rod completes two cycles of increase in length and coming back to its original position. So, in one half cycle of the magnetic field, the rod completes one cycle of change in length. That means if instead of a direct magnetic field, I apply an alternating magnetic field, the frequency of oscillation, the rod will keep on oscillating. It will increase in length, come back to its position, again increase in length. So what will happen? By the time the magnetic field completes one full cycle, the rod will complete 2 cycles of elongation and 2 cycles of change in length. That means it will oscillate with twice the frequency of the applied magnetic field. So that is what is written here. If the frequency of the applied field, we can tune the frequency of the applied field, is made equal to the natural frequency of the rod, resonance will occur and the amplitude of oscillations becomes large, and the rod generates ultrasonic waves into the surrounding medium. This is a simple principle in which ultrasonic waves are generated in this magnetostriction method. So let's look into the construction and working of a magnetostriction generator. It's very simple. This whole part, electronic part, it's a transistor, then a variable capacitor, and this is nothing but an oscillator. An oscillator is a device which can generate an alternating current, source of alternating current or voltage for that matter. So this is fed to the alternating current. These are two coils that is wound around the rod of the ferromagnetic material. So when an alternating current produced by this oscillator, it travels through this coil. Just like a solenoid, what will happen? A magnetic field will be generated, which is applied, which will be along the axis of the solenoid. So it will be parallel to the length of the rod. So basically we need to understand is that this is an oscillator which generates an alternating current. That current is applied to the coil which is wound round the ferromagnetic rod. As a result of the alternating current, an alternating magnetic field is produced which is applied along the length of the rod. So this oscillator, why we are not going into the details of the oscillator, how it produces the alternating current. So basic idea is that we need to understand here is that an alternating magnetic field is applied along the length of the rod and by changing the variable capacitance. So in other words, we can change the frequency of the applied field, applied AC, and hence the applied magnetic field by changing the parameters of this oscillator, by tuning the oscillator. So AB is a rod of a ferromagnetic material. Coils L1 and L2 are wound around the rod which is connected to the electronic oscillator. So this part is the oscillator. An alternating current flowing through the coils generates an alternating magnetic field. The frequency of the applied AC can be tuned in the oscillator to make it equal to the natural frequency of the rod. We are talking about resonance. We can tune the frequency of the oscillator so that the frequency of the magnetic field, alternating magnetic field, is made equal to the natural frequency of the rod. So what will happen? Resonance results in high amplitude oscillations. So these end of the rods, they will start oscillating. Had it been a direct field, it will just elongate because of magnetostriction effect and remain there. But now what is happening? As because the magnetic field is alternating, the rod will elongate, come back, it will start oscillating the ends of the rod. And when resonance occurs, the amplitude of oscillations are very high and ultrasonic waves are generated into the surrounding medium. So this is a simple method of generation of ultrasonic waves. Let's look into what are the advantages and disadvantages of this method. Advantages: this method can be used to generate ultrasonic waves having frequency up to 300 kHz. Also, the generator is simple in construction and also the cost of production is comparatively low compared to the piezoelectric generator, where we have to cut the crystal and those crystals itself are very costly and we have to properly cut it. So it becomes a problem. Disadvantages: the output frequency is affected by temperature. Means it's affected by the temperature in which the generator is kept, temperature of the ferromagnetic rod. The frequency of so what happens? With temperature, the frequency of the ultrasonic waves being generated will vary. That is one issue. The frequency of vibration depends on the material of the rock. So different materials needs to be used for different frequencies. That is another problem. Ultrasonic waves with frequency higher than 300 kHz cannot be produced by this method. So if we need frequencies greater than 300 kHz, the magnetostriction generator fails to generate those ultrasonic waves. So these are certain advantages and disadvantages. Now, let's look into the detection of ultrasonics. We'll move fast through this part. The presence of ultrasonic waves can be detected by the following methods. Piezoelectric method. In the piezoelectric generator of ultrasonics, we use the inverse piezoelectric method for the generation. Means when an alternating voltage is applied across two faces of a properly cut crystal along the electrical axis, the mechanical axis, the two faces perpendicular to the mechanical axis oscillates, resulting in ultrasonic waves. That is inverse piezoelectric effect. In piezoelectric method of detection, what happens? The presence of ultrasonic waves is detected by the phenomenon of piezoelectricity induced in crystals by the incident ultrasonic waves. When the faces of a crystal cut perpendicular to the mechanical axis are exposed to ultrasonic waves along the mechanical axis, they experience mechanical stress, leading to the generation of a potential difference. This is piezoelectric effect. Presence of this potential difference indicates the presence of ultrasonics. Simple like this. What we are doing, we are exposing these two faces to ultrasonic waves. Because of that, the ultrasonic waves, these are nothing but sound waves moving as compression and rarefaction. So they will impinge upon, they will hit the faces of the crystal, resulting in mechanical stress. Because of this mechanical stress, it's like you are applying pressure across these two faces. The opposite faces will develop a potential difference. So this potential difference can be amplified and detected. So the presence of this potential difference indicates the presence of ultrasonic waves. Kunz tube method. This is a simple method in which a tube is there. Lower part of the tube is filled with lycodium powder. This corresponds, this is a what to say, generator of ultrasonics. When ultrasonic waves are incident, these are sound waves. Depending on the length, we can adjust the length. What will happen is stationary waves will be produced. The incident ultrasonic waves will hit the piston and it will reflect back. So as a result, when the length of this tube till the piston is of a particular length compared to or its integral multiple of the incident ultrasonic waves, wavelength of the incident ultrasonic waves, what will happen is stationary waves will be produced inside this medium. Stationary waves means something like this. In a string, stationary waves being produced, something like this region, like this, it moves and it reflects back. And in stationary waves, what happens? There are regions of, this is the region where the amplitude of oscillation will be very high. These are called the antinodes maximum, and at the nodes the amplitude of oscillation is 0. So what happens? When stationary waves are produced, the lycodium powder, it arranges in heaps. So where the heap height is maximum, this indicates the presence of an antinode, and where the location is, or other way around, where the heap is maximum, this indicates the presence of a node, no vibration, and here maximum vibration. So this is written here: when ultrasonic waves are allowed to pass through the tube, stationary waves are produced inside the tube. The powder collects in heaps in the regions of the nodes. Why? Because less of vibration here, so it collects in a heap. Maximum vibration in the medium, so the heap height is minimum or it's 0. The formation of nodes indicates the presence of ultrasonic waves. So why this is happening? Earlier it was uniformly distributed. Formation of these heaps indicates that stationary waves are produced inside this tube because of the incident ultrasonic waves. So if these hips are produced, itself indicates that some ultrasonic waves are incident. It's there. Thermal detection method. This method is based on the principle of generation of heat in the medium through which ultrasonic waves pass. We are talking about it. Ultrasonic waves, they are very highly energetic, and when they pass through a medium, they produce heat. So this thermal detection method is based on that principle. When ultrasonic waves pass through a medium, alternate compressions and rarefactions are produced in the medium. The same as sound waves, they travel in a medium by forming compression in the form of compressions and rarefactions. However, in this case, ultrasonic waves, they also move as compressions and rarefactions because they are mechanical waves like sound waves, but the energy content of these waves are much higher. In the region of compressions, there are more collisions among the particles of the medium than in the rarefactions. As a result, the temperature in the region of the compressions are more than that in the region of the rarefactions. This is something which can be understood. So, when an ultrasonic wave is traveling through a medium, it simply means there are regions of higher temperature and regions of lower temperature. Compressions, rarefactions, compressions, rarefactions. So, we have regions of higher temperature and lower temperature. So, in this thermal detection method, what is done is the temperature profile of the medium is checked. If there is regions of higher and lower temperature in a medium, we can immediately say that ultrasonic waves are there. And this temperature profile is being created because of the ultrasonic waves which are traveling through the medium. So if you have platinum, how to detect this profile? Platinum wire is moved through the medium having standing waves of ultrasonics. Because of the varying temperatures in different regions, the resistance of the wire changes. Platinum wire is a very good conductor of heat, or rather it's very sensitive to heat. The resistance of the wire, platinum wire, is very sensitive to the heat or the temperature of the wire. So as the wire is carried through the region in which there is difference of temperature because of the ultrasonic waves, as the wire is scanned through the region, what will happen is the resistance of the wire will change. In the regions of compressions or higher temperature, the wire will show an increased resistance, and regions of rarefactions or lesser temperature, the temperature of resistance of the wire will decrease. So as the wire is carried through, this is the resistance changes. What is done? This is the platinum wire, and this is the region of compression and rarefaction, antinode and node. So in this region, temperature, this is the node and this is the antinode. In this region, temperature will be more. So profiling of the temperature happens: higher temperature, lower temperature, higher temperature, lower temperature, and so on. So as the wire is scanned through this region, it will show periodic increase and decrease of temperature. That indicates the presence of ultrasonic waves. So that is all we had to discuss in this video. So next video we'll be talking about the uses of ultrasonic waves. Thank you.